Suppose you want to create an ERC20 token with an airdrop distribution. In this video, I'll explain how this can be done efficiently using a Merkle tree and BitMap, and I'll show an example implementation of this in Solidity. First, let's zoom out and recall that Ethereum has at its center the world state. And the Ethereum world state consists of just two kinds of thing. There are regular Ethereum accounts and contracts. So in this diagram, which is from a previous video, I'm attempting to depict that. I have this entire world state, and then within it I have these sort of narrow rectangular sections of data, and these are meant to be regular Ethereum accounts. And then I have these larger regions here that are meant to be contracts. So if we look at one of the accounts, you can see that the accounts have different sort of sections of data. This purple little section here is meant to be the address. Then we have the nonce in blue and the balance in green. And each account has this information and it doesn't have anything else, so it's pretty simple. The contracts are somewhat similar. They have the same sort of basic data. They have an address, a nonce, and a balance. But then they also have some code associated with them. So this is this gray sort of section here. And then they have some storage. So for this video, I have this diagram here where I've got this single contract. It's sort of just a more straight-on view, but similar to the previous diagram. And this contract is meant to be our example ERC20 contract. So we can see here at the top, we have an address for this contract. We have a nonce and we have a balance. Then we have this section of code here. And in the case of an ERC20 token, this code will actually take care of, we'll have the logic for all of the basic things that tokens do. So if you're going to transfer a token, what you really do is you just execute some call or you execute some code on the contract for that token. So you'll send a transaction saying that you want to interact with the code, a certain function, maybe the transfer function on the contract, and it will execute your transfer. And so these contracts, this ERC20 contract also keeps track of a bunch of data. It has this storage section here. And for an ERC20 token, there's some data that is sort of expected to be there. Like every ERC20 contract should have a name and a symbol and the decimals amount. And so these values are kept in the storage for the contract. And for this example contract here, the name is this bit of data here. You can decode it if you want. And the symbol is this. And then for the decimals, there's this value here, which happens to be 18 if you follow this key, this legend that I have here. And the ERC20 contract will also keep track of the balances for all of the token holders. That's actually how the token works. That's how the contract works. Is as we kind of looked at before, like your Ethereum account, it doesn't keep track of your token balances, despite, people sometimes think that because Etherscan or whatever else will display your account with the balances for tokens you have. But those balances are not stored with your account at all. Those balances, what you have to do is you have to go out to all of the different ERC20 contracts that are out there and check their storage, basically, see if your address is in there with some balance kind of next to it. And if so, then you have some of that token. Then for this particular contract, we also have the BitMap, which I'll talk more about in a second, and the Merkle root, which I'll also talk more about in a second. Now, if we're going to want to do our airdrop distribution for our token, we're going to have to first come up with our list of airdrop recipients. And this is done entirely off-chain. We use whatever algorithm, whatever heuristics, whatever method we want to decide which accounts get which amounts of airdrop. So assuming we've done that and we have our list, we then need to decide, we have to find some way to get that information on chain into our contract. And there's multiple ways you could do that. A sort of naive approach would be we could write a function, which only the admins can call, that allows them to update the balances for the various token holders, sort of according to the airdrop list. And this would certainly work, but there's a few problems with it. One is it's sort of just inelegant, and it's going to be pretty laborious. It's sort of a brute force approach, and we're going to have to write some function that has this admin privileges, and then we have to like deactivate it or something later when we're done. Another problem with it though is when we do an airdrop like that, we're going to find that a lot of the accounts that we're airdropping tokens to are actually dead. Like some percentage of those accounts are going to be people who've lost the keys, lost their private keys or whatever else. Or maybe the account is like an exchange account, or it's not like a real account or something. And so if we go through and like brute force sort of update all of these balances manually, we're going to be paying a lot of gas. It's going to be very expensive, and we're going to pay all that gas cost too, by the way. So this whole approach of kind of going in and writing into the storage like that, this would be the push approach. This is like we're pushing all of this data into the state of the contract. Another approach, though, would be a pull approach, where instead of kind of writing to the contract in this brute force manner, we could sort of allow for users to, we can sort of pull into the contract. We can allow the users to claim their airdrop. And then we filter out those accounts that are dead, because the dead accounts just won't claim, right? And we also offload the gas cost to the airdrop claimers, which is kind of nice. And we can do it in a really efficient and elegant way, which I'll explain with the Merkle tree and BitMap. Now, what we can do with a Merkle tree is we can have our entire list of airdrop claimers and the amounts that they're going to claim. We can have that whole thing off-chain, and we can write into the contract storage a commitment, sort of a fingerprint of that data. And because of the properties of the Merkle tree, which I'll explain in a minute, you can submit a proof about the contents of the data. So you can submit a proof saying that you, in fact, are able to claim, 100 tokens, and here's your address and so on. And the contract logic can actually verify that proof and check it against that commitment, that fingerprint, the Merkle root, which it has in its storage. And it can be certain that you either are telling the truth or not. So the way this actually works is, remember, all of this stuff here is off-chain. The contract storage is just this section here. And so all of this is happening off-chain. And what we do is we build this tree, and we have at the bottom of our tree as the leaves, we have the actual data that we care about. So in this situation, we're going to have all of the addresses that we're going to want to give the airdrop to, and some balance or some amount that we're going to airdrop to them. And in this example, I also have an index included with each leaf, but I'll explain that in a minute. For now, we just have these chunks of data. And what we do is we just take those leaves and we first hash each of them. And to do this, we can just concatenate these three values. It doesn't really matter as long as we're consistent. We take those values, concatenate them, let's say, and hash them. So that's what this H is for here. And what we get as a result of that is some hash. And that's these things here. It's a 256-bit hash. So we do that. We take the hash of each piece of data. Then we take each pair, like these two hashes here, and we actually combine them and hash them. And so we do that for each of the pairs here. And then we do the same thing again. We go from this level, we take pairs, we hash them together, and we get a resultant hash. And we do that all the way to the top, all the way to the root. This is the root of the Merkle tree. So if we're the developers building this out, what we're going to do is, we compute all of this stuff, all of this Merkle tree stuff entirely off chain. And it takes a bit of computation, but it doesn't matter because it's off chain. Then we either deploy our contract with this Merkle root written into it, or we have some admin kind of function where we can set the Merkle root, kind of write that into the contract, and then it's there, it's done. Now, you might be asking why we use this tree structure. If all we wanted to do was sort of write a fingerprint of some data on chain, we could just take and have all of this data, all of the airdrop recipients, all of that information. We could just concatenate all of that and hash it and write that into the contract storage. And that would be a fingerprint of the data. But of course, if we were to do that, we wouldn't be able to produce these proofs, which I'll describe in a second, because, if I want to verify that my little chunk of data is in fact part of this larger set of data that was hashed to some resultant hash, if we're going to take that approach and not have the tree structure at all, then what I need to do is provide my data, but also all of the rest of the data, right? Because if any of it is missing, the hash will be completely different. So obviously doing that for a smart contract is going to be incredibly expensive because it's just a ton of data and a ton of computation too. So Merkle trees have this very interesting property where we can prove membership of the initial set of data very efficiently. So if I happen to be this individual here, this is my address, and I have some amount that I'm going to claim, all the data that I have to provide to the contract in order to prove my membership to this set is I have to provide this data, the leaf, which is pretty easy. Then the contract will have logic, which tells it how to do all of this, but it will be able to take the hash of that data. So it will be able to produce this hash here. And I'll need to provide it all of the rest of the data that it needs to get us to the root. So it will be able to produce this hash. I need to provide it this hash, this sort of sibling hash, because it has no idea what this information is. But I can provide it this one. Now it has this one and this one. It can then concatenate these, hash them together, and get this. So that I don't have to provide. But now that we have this kind of right-hand hash here, it needs the left-hand one, right? So I'll have to provide this hash for it, because it doesn't know what any of this stuff is. It can't produce those on its own. And then now that it has the left and right, it can produce the parent. And finally, I'll need to provide it this other left-hand hash, and it'll have then both of these, and it can produce the root. And then it can check the root, right? So it's going to go through that process for any proof that is submitted to this contract. It's going to go through that process. It's going to take the initial data, it's going to hash that, and you're going to provide all the siblings that it needs all the way up the tree until it gets to the root. So each proof of membership to the Merkle tree requires one additional chunk of data, one additional hash that we have to provide per level of the tree, right? And this is actually a really great property because the height of the tree is logarithmic in the number of data leaves, which is great because what that means is that the number of data leaves can be really huge, and yet the height of the tree is just not that big, right? So if you start with 1,000,000 data leaves, the tree is only going to be of height 21, right? So, and if you go from 1,000,000 to 1,000,000,000, so you've multiplied the number of leaves by 1,000, huge increase, right? Ton of data. The number of leaves or the number of intermediate hashes you'll have to provide is only 30 or 31. So the number of leaves can grow massively, and the height of the tree doesn't really get that much bigger. And this is just the simple fact of you take a large number, how many times you have to divide it by 2 before you get to 1, or approximately 1, and it's just not very many times. It's just the property of how it works. So what that means is that the proof complexity is proportional to the log of the number of leaves, which I've just described. So the proof complexity is big O of log base 2 of n, where n is the number of leaves. And so it's extremely efficient. So producing the proofs and checking the proofs is incredibly efficient. And of course, the contract, no matter how big this tree is, if it has 1 billion items or whatever, the contract only keeps track of one root, 256 bits, that's it. But how do we get intuition around why this works? Like, it is strange that I can provide just my data and we take the hash of that. Okay, that's fine. And then I can just tell it a hash. Like, it doesn't know any of this data. I just give it this hash and then I give it this one and this one. And like, I could literally give it anything for those values and it's not checking my work there. And yet it kind of just takes on faith that I've given it the correct values. But of course, it doesn't really take it on faith because, so we can think about how an attack would work. Like, suppose we are this individual. This is our address in here, and we have some amount that we're being airdropped. And the way we might want to, defraud the contract is we increase this number, right? So we change like 1 bit here, and we just add, we change one of these cells to be a 1 instead of a 0 or whatever. So we've increased the amount of tokens that we want to get. Now, the problem there, of course, is we'll provide that data, and it's going to produce an entirely different hash, right? This hash will be different. Okay, now we can provide whatever we want for the sibling hash. So all we need to do here is find some made-up sibling hash that will give us this. Because if we can get this, then the rest of the stuff will work out, and we'll get to the root, and it'll say, you're good to go. Here's your money. But of course, it's effectively, practically speaking, impossible to do that. The only way to, like these two legit hashes are, practically speaking, the only input which is going to produce this output, right? Now that's not true in practice because, depending on the hash function, the hash functions that are used by these contracts can take inputs of any length. So because we're mapping inputs of any length to a finite space, what that means is that there's actually multiple inputs which will produce a given output, right? In fact, there's infinite of them. But practically speaking, it's so hard to find those inputs. Like, it's going to take you till the sun blows up or whatever to find that. So that's really it, because these hash algorithms have this property that it's very hard to find collisions. There's essentially no practical way to fake membership of, the data. Okay, so we have this great data structure, which is super efficient, which allows for individuals to submit these proofs to the contract saying that they are in fact deserving of X number of tokens or whatever. And the contract can verify it, and it's very efficient and it's great. But there's one problem with this approach, and that is we have no way to update the Merkle tree. So if you're one of these airdrop claimers, okay, we already know that you can't defraud the contract in terms of changing the balance or the amount that you're supposed to be airdropped. But so far, we don't have a way to prevent you from simply claiming your airdrop 50 times, right? Because this Merkle tree, it's produced entirely off chain. It's kind of created once, and then the root is, written into the contract state, and that's that. We don't update it, right? So the contract so far would have no way of knowing whether you've already claimed or not, right? So the efficient way to do this is not to try to find some way to update the Merkle tree, because it's extremely complicated and would be more expensive to do that. Instead, what we can do is we can keep track of which of these leaves are sort of done, which of them have completed their airdrop claim. And so ideally what we would do is sort of just set like a Boolean true or false for each of these. We can have an external data structure separate to the Merkle tree, which just keeps track of those Booleans. There's multiple ways we could do this, and the sort of obvious ones that you think of immediately are not actually very good. They're just not the most efficient way to do it. The most obvious and worst solution would be you have a mapping from, let's say, address, like a claimer, airdrop claimer address that maps to a Boolean. But I guess the main problem with this is that when you create a mapping like that in Solidity, you're going to get an entire storage slot for each Boolean, right? So it's, you're defining in Solidity, I want a Boolean that's just like 1 bit. It's actually 8 bits. But because you're doing a mapping like that, it doesn't pack those values into multiple values into one slot. You're actually just going to have an entire storage slot for each address. So another approach would be to introduce this index idea. So if we have some sort of index associated with these leaves, we can take some more efficient approaches. So that's where each of these has this index, and you can see if you go to my legend, I'm counting up. This is the 0th one, 1, 2, 3, 4, 5, 6, 7. So each of these leaves has an index, and this of course is all off chain, right? So adding a little bit of data here, like adding this index, is totally fine. Like it's basically free, it doesn't matter. It doesn't add anything in terms of computation time or like really nothing, basically nothing. So we have an index now. Now we can do, instead of a mapping, we can do a Boolean array. So we could do this, let's have a data structure that is just an array, and it just has Booleans in it. So then we know, okay, we know the index for each of our leaves, and we just set a Boolean, and it starts out that they're all false, as in they haven't claimed. And then if index 0 claims their airdrop and submits a valid proof, we will switch the false to true, and that will say that they've claimed. So this approach is much better, but this is still not the best optimal kind of thing, because in Solidity, a Boolean is 8 bits. So this bool array is actually going to still be using more bits than we need. It's going to look like this. So another approach would be to have an array of uint 256s, not Booleans, but just numbers, right? Just large numbers. And here what we can do is we can kind of, like, each uint 256 is 256 bits, obviously. So we have there 256 little Booleans, essentially, right? So if we can basically just find a way to index, like write some logic so that we're kind of indexing properly. Like we want this first uint 256 to essentially hold the Booleans for our first 256 leaves in our Merkle tree. So what might the logic for this actually look like? So we need some way to kind of index both across the uints and within them, right? So for example, if we have the number 525, this is our index. So what we do is we take, and first we need to find which uint that bit lives in. And the way to do that is pretty simple. You take 525 and you do integer division by 256. And that's basically just going to say, if this number was like less than 256, it would be in here. So bit, 20 is going to be in here for sure. Bit 300 is going to be in here, and so on. And the way to actually calculate that is you just take the number, integer division by 256, and that will tell you the index of the right integer. So in this case, it's 2, which is this uint. Then we need to find where in that uint is the bit that we care about. Where is bit 525? And the way to do that is you just take the number 525 and you do mod 256. It's really just like division with remainder. Like the division here for 525 is, the integer division is 2, and then the remainder is 13. So that brings us to our bit of interest, and then we just flip the bit. We use some bit masking for that, and that's it. Now, if you look at how OpenZeppelin, for example, actually implements BitMaps, they don't actually use uint arrays as their underlying data structure. Instead, they use a mapping. And at first, I didn't quite understand why. It's like, okay, the uint array is perfectly fine. It has this indexing, which works great. And then we have our integers. and it's efficient. No bit is wasted, right? In the case of the mapping, we map from basically like index values. So it's effectively functioning just like a integer array. I didn't understand why we would use the mapping instead of the integer array. In terms of space, they seem to be equal. Here we're just storing each integer. Here we're just storing each integer, because of course these keys are not stored in the contract anywhere. And my first thought was, okay, so dynamic integer arrays, we need to track the length of the array, right? So a storage slot is used to keep track of the length of this thing. So in addition to all of these, which each, in this case, each are going to use a storage slot, we also have to use another storage slot to track the length. But that's actually the case for mappings as well. We don't track the length, but a storage slot is set aside for the mapping. And I'll link below, and you can read how that actually works. The slot number is concatenated with the key, which tells you where to go to find the value, which storage slot the value should be in. So it seems like they're actually the same. Like the mapping is not more efficient. I don't see why you would use a mapping, but I think the tiny little efficiency gain is that in the case of a mapping, that extra slot is actually kept blank. So with your dynamic array, that extra storage slot keeps track of the length, which is obviously non-zero. And for the mapping, we keep the slot 0. So that should be cheaper. It should be a tiny little bit cheaper because you're not writing the storage slot to a non-zero value. So you should be a little bit better off. And so at the end of the day, what our bitmap in this example might look like is something like this. So here's the full bitmap in the storage. And because this example only has 8 data leaves, there's only 8 bits to keep track of. So this 256-bit storage slot has just these two values, which are non-zero. These happen to translate to 5B, and this is like the hex representation of those values, but we're treating them as bits. So we want to kind of, convert this or just look at it differently. Instead of 5, we want to see the full nibble, the full 4 bits. So 5 happens to be 0, 1, 0, 1, and then the B is 1, 0, 1, 1. So we can see that set of bits maps to our data leaves. So each data leaf has its bit, and here you can see those same values, 0, 1, 0, 1, 1, 0, 1, 1. And so the combination of these two data structures, the Merkle tree and the bitmap, gives us this complete solution. Okay, so now we will look at some code, and I'll go through this pretty quickly, but first of all, here is let's start here. So this is the airdrop token.sol, and it's super straightforward. What we have is it's an ERC20 token, so we inherit that from OpenZeppelin. And then we have our Merkle root here. So this is, a array of bytes, 32 bytes total, so 256 bits. But it's just a chunk of data. Then we have our bitmap. So from OpenZeppelin BitMaps, we have the bitmap, which is a private thing, and we call it airdrop list. Then we have the constructor, which sets the Merkle root to whatever we pass in. Then we have our claim airdrop function. So this one we pass in the proof, right? I'll talk about that in a second, but we pass in a proof, an index, and an amount. So what we're passing in is all of the leaf data. The address is pulled from message.sender. So the message.sender address plus these two is the total leaf, right? So we pass in that leaf data and then the proof. And the proof is an array of bytes. And so that is where those sibling hashes will be, right? And so it's pretty simple how this works. We go through and we first of all check the bitmap and see if the airdrop has already been claimed. We check the index, and if it's already been claimed, we just revert. And otherwise, we verify the proof, which I'll talk about in a second. Then we, in the bitmap, assuming this worked, right, we go to the bitmap and set the index to true. And then we mint the tokens. So then the person, if all of this passes, the person gets the tokens. And what the verify proof function does is, again, pretty simple. It takes the proof that is passed in, then all of the leaf data. All of the leaf data is here. And you can see that message.sender is passed in, so that's where address comes from. And all it does is calculate the leaf value, which is, take address, index, and amount, basically just concatenate them, hash them, and hash that again. I don't actually know why this implementation wants to hash those contents twice. I'm assuming there's some reason for it. I'm not entirely sure, but that's what they do. And then we just take that leaf and we call verify. So there's obviously some magic that's happening in here. It's just checking the proof, right? It's taking and doing that repeated hashing all the way up to the root. And so it needs to know the Merkle root, and it needs to know the proof and the leaf, right? So the proof, of course, has all that information, those sibling hashes. The root is the root, and the leaf is the leaf data hashed, twice in a certain way. And yeah, we can see I have some tests here which should work. And it does work. So yeah, again, pretty simple. Like, we have the Merkle root here. I'll show how that's calculated in a second, but we have our root. We create this, this contract. We deploy the contract with that root. Then to test the claiming of the airdrop, we just supply. These are the sibling hashes. So I'll show where those come from, but these are the sibling hashes, and we just put those into a bytes array. So there's 3 items. Then our index is 0. The amount we're going to claim is this, and we just assert that we don't have any tokens. Then claim the airdrop as this account, and we can assert at the end of that we do have the tokens. So where all of that stuff is actually coming from is kind of interesting. I hope that's, maybe I'll do this. So first of all, we can create the Merkle tree. So this is just JavaScript. This is from OpenZeppelin, but this is just JavaScript, right? And we're just taking and creating the tree. So here are all of the values in the tree. These are all the leaves, right? Each array here is a leaf. There's an address, there's an index, and here is the amount. So we provide all the leaves, and then the, this code in here is going to actually produce the tree. It's going to take and, like, here we're just telling it, like, what should these values kind of be? What are these values? Like, these indexes are going to be expanded to uint 256, so they're going to be padded with a bunch of zeros, and these amounts will be padded with zeros too. And it basically just produces the tree. So it's going to, oh, that's the proof. Create Merkle tree. So that's going to produce the root, right? When we run this, it gives us the root, which is right there. And that is what this JSON file is. And we can format that. So we have, this is the tree. And actually, if you actually go through this, first at the bottom here, you have all of the hashes of the leaves. And then at the top, like at the top, you have the root. See, it's the same A363, A363. And down here is just these are just the intermediate hashes. So like, that's it. The same diagram that I showed, that's what this is, just with different values. And we can see all the values here, and That's pretty much it. Then to create a proof, so if you are the deployer, like the creator of this contract, you're going to do all of this, decide this address is going to get this many tokens. This is all done off chain. This is the stuff that you do, right? You do all that. You get your root as a result. You're going to write that root into your contract one way or another. That's what I was doing here in this test. And you will circulate the list of these, these values, the airdrop claimers. You'll circulate that, allow people to see it. I mean, really, you'll have some front end code that kind of deals with all of that. But then you put the root on chain and in state, and there's a way to for the contract to verify those proofs. Now, where the proofs are actually constructed, this this JavaScript here is doing that. So all we do here is basically just we tell this code, like this code has the entire tree, right? It loads in the tree.json, and then we're really just telling it like, okay, this is the address, this is the leaf that I want a proof for, right? And then get proof really just it really just gives you the values that you need. Like, it's not really generating a whole lot. It's really just giving you the necessary intermediate values, the intermediate hashes, and that's these three here, which is exactly like in the diagram, right? If you're this guy, you need to provide 1, 2, 3 extra hashes. And so that's what this is. So then as a user, you would have some code that you interact with, which would give you these hashes. You are like this account, so you get those hashes, and then you would create a transaction to the token contract and providing, something like this, those hashes in a list, as well as any other information, and that's it. That's how it works. Okay, thanks for watching. If you have any feedback, let me know. The code that I use in this video will be uploaded to GitHub, so I'll leave a link for that below. And next video will be on, I'm not sure what. I do want to do an Ethereum proof of stake video series at some point. It's just a lot of work. And so, yeah, if you have a preference, let me know. And thanks for watching. Peace.